Hello and welcome to the 51st session of Porous Media Tea Time Talks. We are part of Interpol Young Academy, and with this webinar series, we intend to give the chance to young researchers to present their research to the wider scientific community around the world, and we would like to have a diversified topics of forest media in different applications around the world. My name is Mohammed. I'm a researcher at the University of Oslo, and today with me I have Chiara from Politecnico Milano and Sang from University of Minnesota. Without further ado, I would like to introduce our first speaker, Anna. She's a PhD student at the Luleå University of Technology at the Department of Engineering, Sciences and Mathematics. Her research is part of the Drizzle Center, a center for stormwater management dedicated to enhancing stormwater management practices in Sweden through innovative solutions and concepts. The focus of Anna's work is on fluid mechanics analysis, working under the guidance of Professor Staffan Lundström, Sofia Larsson, and Lion Landi, and with a close collaboration with Professor Hans Åkerstad. Thank you, Anna, for joining us today, and the floor is yours.
Thank you for having me. Hello, everyone. My name is Anna Barcot, and I'm a PhD student at Luleå University of Technology. Today, I will be talking about fluid flow analysis within sponge-like porous bodies, which is the title of my PhD. Also, I want to just highlight that I've been doing my PhD for 1 year now. However, in this time frame, we have conducted a lot of research, and I'm happy to be talking about it today. First of all, I would like to highlight that my research is part of a Drizzle Center of Excellence for Stormwater Management project, which is led by Chair Professor Maria Wiklander. The project was established in the year 2017 and consists of a total of 13 partners. And it is also one of the Vinnova funded competence centers for research important topics to Sweden. The aim of the project is to further advance the stormwater management solutions, research-based solutions more particularly, when it comes to flood control, pollution control, and also capturing opportunities when it comes to runoff benefits. The research is divided into 3 main areas: stormwater quality research, stormwater quantity research, and integrated solutions. My research work is part of the research stormwater quantity research. And just to highlight the importance of stormwater management research in Sweden, here you have a photo which was taken in May of this year in the north of Sweden, which depicts one of the worst floods which has been seen in Sweden in the last 50 years. So it shows that the stormwater management is really important research of topic in throughout the world, and in this case we are focusing on Sweden. As part of our stormwater quantity research, we have developed the sponge-like porous bodies concept, and my research will further focus into exploring further the potential of this concept, looking more deep into theoretical and numerical analysis and modeling, as well as, of course, conducting further experiments. I have also provided a list of the published research on this concept to this date. So if you're interested in more details about the concepts, the modeling, and all the details, you're free to look at and read all of the research articles. As you might be aware, that urbanization in developing areas affects the hydrological cycle, and of course increasing the runoff and risk of floods. Mainly by reducing the abstractions. So here, with the modern drainage system, the main idea is to restore the pre-developed catchment conditions by increasing actually the water abstraction. And of course, when we talk about these type of modern designs, they can be developed at various scales. In particular, when we talk about sponge-like porous bodies, we're talking about lot scale measures. So what are sponge-like porous bodies? Well, the concept was primarily developed by Professor Stefan Lundström, Professor Maria Wiklander, and Professor Jiri Marsalek here at the Luleå University of Technology. And the intended applicability of the sponge-like porous bodies concept is to operate alongside already existing lot scale measures, some of the best practices, for example, green roof or gray roof concepts. The sponge-like porous bodies, they're divided into two main types. We have the upflow model, which is presented here on the figure in B and C, consisting of two types, intermediate height and low height structures. And also we have a downflow model presented in figure A. So the main difference between the models is that when the downflow model comes into the contact with the rainwater, so the rainwater comes direct contact with the absorbent material of the model, it swells vertically, and it is intended to be placed on rooftops, on ground, playgrounds, and larger areas. Whereas the upflow model, as I already mentioned, there are two types. The intermediate high structures, most commonly 1 to 2 meters, are placed around solid objects, and the low height structures, usually around 0.2 meters, are growing directly from the ground, kind of mimicking a growth of a plant. It is very important to say that the choice of material in this concept is essential. We still have not finalized our choice of the material, but we're of course planning to conduct more experiments to determine the best material. But for now, we do talk about the potential of use of hydrogels. In the downflow model, we're looking at swelling of hydrogels, and of course in the upflow model, looking at the porous rods consisting of nanofibers. So to model the flow into the sponge-like porous bodies, into the absorbent material, more specifically of the sponge porous bodies, we begin by establishing, of course, the governing equations. So in particular, for the downflow model, we look at the diffusion equation. Here it is presented its most general form, and where theta presents the water concentration and d is the diffusion coefficient. The diffusion coefficient we consider to be constant. Alongside the diffusion equation, we can also derive the volumetric uptake, and further we can express it in terms of also the concentration. So we have a suitable set of equations. Further, when it comes to the numerical modeling, we particularly when it comes to the absorption capacity, the larger the interface surface area is, the better the absorption is. So in this particular study, a prismatic block is taken, and within a periodic arrangement of small cavities of cross-section small b times small b, and hence so this is a sketch presenting the increasing of the absorption surface area, and so looking, and also with the dashed line indicating a unit cell. So we therefore further obtain our numerical results by with a suitable set of equations, looking at the unit cell with suitable boundary conditions. We go into the COMSOL multiphysics software and we obtain results. Of course, here we can vary the diffusion equation, we can vary the parameters, such as, for example, the thickness of the material, the absorbent material, then changing the geometry of the cavities, and also the thickness, small h, of the cavities, and we can obtain different volumetric uptake results. Similarly, for the upflow model, here we have also the governing equations of Darcy's law alongside the incompressibility, where U is the velocity, phi is the porosity, K is the permeability, and P is the pressure. The flow is mainly driven by the capillary action, and here of course the capillary action can be expressed as the very famous formula and Urine's law, and of course looking at the by varying the in particular here for us, the pore radius, as I have mentioned previously, we considered that the upflow model is consisted of porous rods made of natural fibers or hydrogel fibers. Here, as we change the radius of our rods, we obtained, of course, different water uptake. So also we also changed the permeability, of course, depending on the material we use, also the porosity, we obtain different solutions. Here, of course, we also further compute the with a governing set of equations, and going into the MATLAB, we perform a semi-analytical fashion. We obtain results, and for different parameters, we obtained different solutions, and we take the we of course look at the best performing parameters, which will later compare to rainfall data, which I will talk in the next slides. Also, it is just important to emphasize that here, in this particular study, we were looking at the intermediate type of upflow model, where we have a solid object and surrounding with a porous annulus consisting of two different porous materials, where Ri represents the inner radius of the pore material and Ro the outer radius of the porous material. As I have already said, by choosing we also want to check the best performing model and verify its applicability in real event scenarios. In this case, we have in this study, previous study, it was the rainfall data was taken from the Swedish precipitation records for two events in the two locations of Sweden. In the two exact events are, we have the so-called uniform intensity or the block rainfall of 16 minutes of average duration with a return period of 1 to 10 years. And in another event, same event, however, here we include a high intensity burst of 5 minutes with, as I already said, with the two locations in Sweden. So for the downflow model, as mentioned, we vary different parameters and we take the best with the best performing the downflow device, and we compare it to this rainfall inflow data. And from the results, it is evident that the model can very well capture all of the rainfall. When it comes to the upflow, however, on the other side, does not capture all of the rain inflow. Does not capture all of the rain inflow water. However, it shows to capture great amounts of water in quite short periods of time. And we, of course, if we take more than one unit cell per, here it was, we chose different areas that were contributing areas that were looked into for the model. If we take more than one unit cell per area, we can of course ensure that we have a complete capturing of the rain inflow water. We then further move from, so up to this point, we have talked about the initial theoretical and numerical modeling of the sponge-like porous bodies, and we would like to extend further into considering particularly the performance of the upflow model when surrounded by surface water, and also considering soil infiltration. The difference here compared to the previous studies is that here we have a full cylindrical model consisting of the same material as the previous upflow model. However, here, as I said, we consider a full cylindrical model, and with the same conditions, we assume that there is no swelling, no deforming, no water flux at the lateral boundaries of the model. Very simple. We also consider also, of course, that we have homogeneous and isotropic porous media, which was also in the previous studies. And for the description of the flow, we come to the Laplace equation. Further, by applying the uniqueness theorem due to having Laplace equation and no flux boundary conditions, it is very easy to check that the solution of the flow uptake will be one-dimensional. So we only have the vertical uptake of the water, no horizontal movements within the model. since we're also here including the infiltration of water into the soil, we take a green empt model, with a sharp wetting front, distinctly dividing the saturated from unsaturated region. In a similar manner, we here in order to ensure that we have zero flux boundary conditions, we assume infinite domain with periodic arrangements that, due to symmetry, ensure that we have zero flux of no exchange of water at the boundaries. So again, we come to the Laplace equation, and also no horizontal movements, only vertical positioning of the water into the soil. So further, now that we have described the equations, we also have to include the movement of the surrounding water. More precisely, we have to include the conservation of volume. So here, it is important to indicate the difference of the rain when it comes to rain compared to previous studies. We take the same rainfall data as in the previous studies. However, here we consider that the rain inflow is uniform, and it lasts for an average duration. So it lasts for a period of time of 1 hour. That was what we were looking here into this particular study. We have studied 4 different cases, and here in this table you can see a description of each of the cases. In case 1 being the most simple and case 4 being the most complicated. Case 1, when it comes to modeling. Case 1, we have impermeable ground, and we do not consider that there is any rain inflow. For case 2, we consider that we have rain inflow, and for case 3, we do not assume that there is any rain, and we include that there is soil infiltration. And for case 4, it considers all of the factors. So we have rain and we have soil infiltration. Interestingly, the system can be a set of equations when, of course, the details, as I already have said in the first slide, you can check the paper and all of the derivation details are provided there, but the system can be expressed in terms of the surface ratio, which is equal to the surface area of the model divided by the surrounding surface area of the ground. Interestingly, the dynamical term can be neglected. So in the long-term analysis, we have verified this by deriving an analytical solution, which is in case 1, and also we have checked this with numerical simulations, and we have compared what happens when we include and or ignore the dynamical term in our system. And we have checked that only for order of milliseconds is that the dynamical terms become important in the changing of the water uptake. So for our analysis here, we are not interested in the initial stages, but rather the long-term analysis. So this term here in the system, so dynamical pressure term, can be ignored. Therefore, this also leads us to the next component, which is the head losses that can occur during the water uptake into the model due to the change of geometry or the sudden narrowing, where we have to include the friction losses. We can express the head losses in terms of the friction coefficient psi, which when included into the system will again be just added to the dynamical term. And as I have already explained, we have verified the dynamical term can be neglected in the long-term analysis. Therefore, the friction losses can be neglected and also in the long-term analysis. So if we're investigating the flow at the initial stages, these are definitely the factors we cannot ignore. However, for what we aim here, looking in over longer periods of time and overall just checking the absorption and water uptake of our models, this is not of primary interest. So further, we now come to the results. So we compute results for each of the cases. Again, following the physical and mathematical modeling, which I have previously explained, and setting the boundary conditions. And we can, again, in a semi-analytical fashion in MATLAB, we can resolve our system numerically. But in the case of one, we can also resolve it analytically, and we have verified that the results are in a perfect match. It is interesting. I want to emphasize that when we talk about efficiency in this study, we're talking about the time absorption time, meaning the time for which the surrounding water or the flood will be completely absorbed by the model. So that means when the H is 0. So in case one, as I said, is the most simplest case, we can derive the analytical solution of the absorption time in which you can see here. And from the condition from the logarithmic condition, we can derive the critical value. For the initial pond depth, also we can derive the critical value for other parameters. If we, for example, fix the initial pond depth, we can also derive the critical value for other parameters such as the surface ratio or the porosity. In this case, I'm talking about the critical value of the initial pond depth. And also when we performed the numerical simulations, we got the same value. Yes, and also here the Z represents the capillary height, which is the capillary pressure divided by density times the gravity. So when we plot the results, it is what I have just explained, that if the initial pond depth, so here we have the results for different pond depths, if the initial pond depth critical value is surpassed, which here in this particular case is 0.5379. And for example, if we take 1 meter, which is this blue dashed line, you can see that the water will never be absorbed, that the model will not be able to fully take the surrounding water. Whereas for lower than critical values, it is able to absorb. And similarly, the similar analysis is performed for the porosity values. Now in case 2, when we add the rain, we consider now that we have rain, still the ground is impermeable. Of course, we expect that the rain will increase the absorption time, but how much exactly we will see now in the results. But just before that, I just want to indicate that here the modeling becomes somewhat complicated when we include the rain during the 1 hour while the rain is falling. We get this system of equations, and when we exclude the rain, we have this kind of modeling. Also, we can only obtain the analytical expression after the rain has ceased, which in the same manner as we have did for case 1. And here are the results. As I said, the rain will definitely increase absorption time, and dramatically so, where in the previous, in the case 1, we had that it was around 2,500 seconds for 0.5 meters of initial pond height, and here for 0.5 meters, you can see here it is 9,000 seconds. So the effect of rain does increase the absorption time considerably, and it is the same here for changing the porosity. For cases 3 and 4, we include the soil, and here is the modeling, and of course it becomes much more complicated. We have also looked into the different soil types. Mainly we have chose the soils based on the Swedish digital map, which are the most common soil types. We chose sand, silty soil, and clay for this particular study, and we analyzed. And of course, from the results plotted, it was obvious that the sand is the best performing in terms of absorption. As I said, the modeling becomes here much more complicated. I'm not going to go into details. This is just shown for case 3. Of course, for case 4, we need to include rain into the system. If you're interested in more details, of course, you can find it in the paper. Of course, as expected, we expect that the presence of soil will reduce the absorption time considerably, but of course, the question is always how much exactly. You can see that for 0.5 meters of initial pond depth, here the absorption time is significantly lower, and also the same when we vary the porosities. Also for the cases 3 and 4, we also wanted to track the efficiency of the model. So we wanted to see in terms of absorption time when we include or when we don't have the model, what is the efficiency? How much does model help in the, how much does the model, how efficient is the model when it comes to absorption compared to the soil as a sole absorber of the water? So we found that in case 3, it's 0.857. And also in case 4 that it is 0.88. So basically in case 4 we include the rain, and we do expect that yes, it will be having higher efficiency. Here is just a summary of all of the results, and it's just to summarize what I have been explaining so far, that in when it comes to cases 1 and 2, that the absorption time is much longer than compared to cases 3 and 4, where we include the soil. As here we can see that the permeability of the ground plays a crucial role, and therefore in stormwater management, when it comes to stormwater management, this is a very important factor when we think about building, urbanizing the ground, that as we reduce the permeability of the soil, we do have a problem of the absorbing of the large runoff volumes or floods. So here we can see how much particularly for case 2, when we include the rain and when the soil is impermeable, compared to when you have the rain and the soil is permeable, the difference in the time absorption. The same can be said as when we increase the rain influx. You can see here that when the critical value for rain influx is surpassed here, that the model is no longer able to absorb fully the surrounding water, whereas in case 4, it is after just 400 seconds. So the permeability of the soil does play a crucial role in the absorbing of the water pond or of the surrounding flood, which is supposed to mimic a flood. Also, I want to say that I forgot to mention that when we were picking the values of the pond, we were looking at the study investigation carried out in Malmo in Sweden. What was the average flood height? So we were relying on that data, but here is just to conduct a study to further look into this potential of the model and how much it can help in the relieving the pressure, as I said, on the existing drainage systems. Further, we also plan on to perform more experiments when it comes to choosing the material. We have already done certain experiments on the numerous experiments on the available hydrogel material that we had, which it's nanofibers derived from wood. We also performed the material scanning using X-ray tomography, and we have seen that the water absorption uptake is very high, as also you can see here. However, the problem was when after the absorption experiment, the material cannot be reused, which is not what we want. We would like to make the concept sustainable and to be able to be reused, of course, after numerous applications. So we're still looking at the material. Even though this particular hydrogel is not of interest, we are still focusing on hydrogels as potential material. So we are trying to now collaborate with the material department and select the perfect material for this concept. Yes, so thank you for listening, and thank you for your attention. If you have any questions, I would be happy to answer.
Thank you very much, Anna, for your talk. It was really, really interesting. I mean, you can definitely tell that you put a lot of effort in driving all of these equations and these analytical / semi-analytical solutions. So, I mean, I'm asking the online audience to type their questions in the chat. So if you have anything to ask to Anna, you can just type and I will read the questions out loud. And in the meanwhile, if we have some questions in the studio, or I can start with a couple of my own that are more like curiosities. So first of all, you mentioned two kind of systems, right? One that is like more horizontal, kind of sponge-like body, and another one that is developing in the vertical direction. So I was just wondering, maybe you said it and I just missed it. So if you were in a practical situations, which one would you recommend to use it, like the horizontal or vertical one?
Yes, depends on the application. For the downflow model, can be used in more larger areas. So in that way, you can produce larger interface surface areas of the absorbent material of the downflow model. For the upflow, it is intended to be used in more space-limited areas where it is not possible to have more permanent solutions. When it comes to drainage systems. So here, for example, as I already said, around trees, around lampposts, it is intended to be used in applications where space is limited, and especially in urbanized areas, this is a huge problem. So we believe that this kind of solutions would relieve a lot of stress on the existing drainage systems because yes, it would definitely help in reducing the floods and runoff volumes in these such limited areas.
Okay.
Yes. Yeah.
Then I have another question, if we have time. That is, well, it seemed to me that you had like a lot of, let's say, that you need a lot of information if you want to apply your model in a real case study, right? In terms of the, let's say, boundary conditions of the real system, like the level, the height of the water, the intensity of the rain, a lot of parameters. And I was just curious, how can you get all of this? Is it easy? Maybe in Sweden you have some databases where you can find this kind of information concerning the ground parameters and everything, or is it the challenge? Or I don't really know. I mean, I was just curious if you can just comment on that.
Yes, definitely. The thing is, it is quite difficult to get exactly. So first, what we aim is to just start with the modeling and set the conditions, which, yes, they are more simple, but they do give us an idea of how it would be in actual more practical case. But yes, obtaining this kind of data from the database, I did manage for this last paper, which I was talking when I was looking, for example, at the flood information in Sweden, or when I was looking at the participation events, and it is quite available information.
Okay.
However, I do believe that so what our group particularly is more fluid mechanics focused. So we do have a collaboration with other departments such as civil engineering, which is actually they're the main part of the project because they're also part of the stormwater quantity research, but they do more like green roof type solutions, lot scale mainly, and other types of solutions. So we collaborate with them and then of course they can provide us more with this kind of practical solutions. But for now, it is I would say the concept is it's in early stages of development, and for now I would say our next step is just to find the most suitable material for our solution, and that is maybe quite challenging actually, because we would need someone to actually produce in a way a material for us. So we're planning, as I already said, maybe a collaboration and then get more materials. So for the beginning, just to have the materials, and then we can maybe start, including more practical, maybe even on-field experiments. But yes, when it comes to parameter availabilities, and yes, I think it's it's not that difficult to gather the data. And as I said, we have collaborations with other departments, and they help us a lot with this. So. And my focus of the study is more fluid mechanics, yes.
Great. Okay, so we have more a comment than a question. That is, I will put it online, okay? So yeah, it was a really interesting presentation. And
yes.
Tushar is wishing you luck for your PhD. So I think that we can now just move to our second speaker. So our second speaker would be Iman Vaezi. Iman holds a Master of Science in Geotechnical Engineering, and he worked for several years in the industries before starting the academic path. Currently, he's a research assistant at the Spanish National Research Council, and he's a PhD candidate at the Technical University of Catalonia. His research tackles the mechanisms that induce seismicity due to fluid injection in enhanced geothermal systems. And well, with this, I will not spoil anything more, and I will just leave the floor to Iman. So Iman, the floor is yours.
Iman, you are muted and you have to unmute yourself.
Oh, sorry. Thank you, Chiara, again for the introduction. Good day or good night, everybody, wherever you are. Today, I'm presenting on behalf of my colleagues in this project from the Spanish National Research Council and Geoenergie Suisse. I'm working as a member of GeoRest research group, laser point. Under supervision of Dr. Villarasa, GeoRest's goal is to develop a novel methodology to predict and mitigate induced seismicity. My research is related to coupled processes during the stimulation of enhanced or engineered geothermal systems and pertinent induced seismicity. A global trend toward CO2 and nuclear-free technology has prompted interest in deep geothermal energy as an alternative renewable source, free from seasonal fluctuation and with potential for continuous energy output. Regarding CO2 emissions, coal is the dirtiest of fossil fuels, emitting more volume of CO2 per joule produced than both oil and natural gas. In the present day, solid and liquid fuels dominate emissions, although contributions from gas production are also notable. And around 1/3 of this emission is for electricity and heat generation. So we know to which section we should tackle. So why use the electricity either by burning fossil fuels or even using renewable electricity resources when we could tap heat? The core of Earth is 6,000 degrees Celsius, the same temperature as the surface of the sun. So anywhere in the world, if we drill deep enough, we can reach a temperature far beyond what we need to produce baseload clean energy. So of course, when we talk about the subsurface, we should talk about the fractures too. The functionality of geoenergy applications is highly dependent on the presence of fractures. Fractures provide a permeable pathway for transportation. Therefore, they present both problems and opportunity for geoenergy applications. For instance, fracture permeability should remain as low as possible in underground storages, but in crystalline rock, it is sought to be increased in enhanced geothermal systems, which is the focus of this presentation. So what is an enhanced geothermal system? The concept is simple. Inject cold water into the subsurface and extract the heated water for our usage. A naturally occurring geothermal system, which is known as hydrothermal, is defined by three key elements: heat, fluid, and permeability at depth. It means to generate power from natural geothermal systems, we need abundant heat found in the rock at depth, plus enough fluids to carry heat from the rocks, and a small pathways to conduct fluid through the hot rock. However, in most cases, there are problems. Despite the presence of heat, sometimes conditions are not ideal for power generation from natural geothermal systems. In these cases, we have insufficient fluid to carry the heat and limited pathways to conduct fluid. As a solution, a man-made enhanced geothermal systems can extract the abundant heat resources tens of thousands of meters below the surface and put it in a good use. This would require fluid injected from the surface as well as the permeable pathway enhanced by injected fluid. To enhance permeability, injection-induced shear slip and dilation of a pre-existing fracture is one of the most promising approaches for extracting geothermal energy from hot, ultra-low permeability rock at depth. It is referred as shear stimulation or hydroshearing in EGS. This fracture self-propping by asperities is considered an effective means of permeability, permanently permeability enhancement. At the beginning, fractures are normally closed. During the stimulation, when the pore pressure reaches the jacking pressure, the initial tight fractures become open, and which leads to permeability enhancement. And consequently, pressure drop, which allow to inject more. This procedure forms a loop of hydromechanical coupled processes. But there are consequences, and this is induced seismicity. Induced seismicity refers to typically minor earthquake and tremors which are caused by human activities that alters the stress and strains of the earth crust. Activities such as geothermal energy, geologic carbon storage, or hydraulic fracture techniques. If felt, induced seismicity has a negative effect on public perception and may jeopardize geoenergy infrastructures. And even it has led to cancellation of several projects like EGS at Basel and Pohang. It is necessary to reverse the damage that these incidents cause to public perception, since without energy, technology, climate neutrality cannot be reached. So forecasting injection-induced earthquake is a big challenge that must be overcome through a combination of field measurement and simulation that take the relevant physical processes into account. To study hydroshearing in EGS, we have modeled a stimulation process at the Bedretto Underground Laboratory for Geosciences and Geoenergies in south of Switzerland. The overburden directly above of this laboratory is approximately 1,500 meters, providing conditions that start to resemble realistic EGS system. This study presents a numerical modeling and analyzing of the hydraulic stimulation performed in the borehole MB1 in February 2020. We have developed a numerical model of this field experiment in a fully coupled hydromechanical simulator, CodeBright, a 2D plane strain model including all the wellbores and identified fractures. The model has a large extension to avoid boundary effects and is progressively refined toward the center, which represent the lab and its vicinity. The major fractures and shear zones, which were identified through borehole logging and geological structural analysis, are included in the model. We have carried out 3 numerical models with increasing complexity in terms of material constitutive law and coupling of permeability and fracture aperture, which we believe they get closer to the actual conceptual model. The stimulation test is modeled by injected water through an isolated section of the borehole AB1 at the measured depth of 267 meters into the fracture. Isolation was achieved by a double packer, which is also included in the model as a very low permeable section of the borehole. So we had 3 numerical models. The first model, temporal evolution of the fracture permeability, has been manually calibrated, homogeneous in space, yet variable in time, to achieve a reasonable fit of available measured pressure evolution at the injection interval. The red line is the calibrated permeability, and the solid blue line is the field pressure measurement, and the dotted blue line is recorded injection overpressure. The fracture has been modeled as an elastic continuum medium with homogeneous hydromechanical properties. The second model incorporates an embedded model in which permeability is a function of volumetric strain in the fracture. In this model, fracture permeability varies with distance from the injection interval and remains constant and equal to the initial value far away from the injection well, where pressurization has not dilated the fracture. To account for permeability enhancement induced by dilatancy due to the shear slip of the fracture, we use a viscoplastic constitutive law that includes dilatancy and strain softening in the third model. Here, lambda represents either cohesion or friction angle. Eta is a function of a plastic strain and can reduce peak strain until the residual strain. Eta star is a value of the softening parameter controlling the transition between the softening and the residual stage. So for the result, it's a bit crowded, this slide, so let me explain it step by step. So we have two panels. At the top, we have a pressure evolution at the injection well, as well as the injection flow rate. The bottom panel is the evolution of the permeability. So we had three models with the three different line style, and the black line is our field data. First model, the green dot, does a good job in terms of curve fitting. It was supposed to, because we had collaborated to do that. In the second model, which is employing embedded model for the permeability, in a certain point there is a discrepancy in the pressure evolution as the fracture reaches its yield point and undergoes shear slip and dilation, and consequently permeability enhancement. However, the material is elastic in this model and thus cannot reflect the mechanical response properly. So the generated strain is smaller than the actual one, and the embedded model yields less permeability enhancement than the actual quantity. As a result, the calculated overpressure is higher than the field response due to the lower permeability. Therefore, third model, this one, which utilizes viscovelocity constitutive law with dilatancy and strain softening, it can reproduce the temporal evolution of generated injection overpressure of the field test better than the previous model, especially during the last injection phase. This model allows to simulate fracture and reactivation and yields an additional permeability enhancement when compared with the elastic model. In this case, permeability enhancement is given by both elastic and plastic strains as shear slip accumulates. Plastic strain further enhances fracture permeability, leading to a smaller pressure buildup and thus to a better approximation of field data. The main issue with the first model, the calibrated model, is that fracture permeability is homogeneous in a space at any given time. The middle panel is the permeability profile along the fracture at two different times, before the black one and after the red one, after failure. Using an embedded model, which is a function of volumetric strain in the bottom panel, shows that permeability increases locally near the injection well, within the pressurization region of the fracture, and is lower away from the well. The pore pressure buildup along the stimulated fracture mainly occur within the reactivated region with irreversible strain in the highlighted green color. This plot accentuates the fact that even though the first model can reproduce the same pressure at the third model at the injection well here, pressure profile are quite different. And the first model overestimated pressure buildup along the fracture especially out of the reactivated zone. We chose a point in the fracture near the injection well to monitor the stress path, which represent the successive state of stress during the simulation test. The initial stress is stable and is directed toward the failure surface as pore pressure increases with increasing deviatoric stress. Failure occurs under compression during the shear drop until fracture reactivation. There are some microseismic events which are recorded in the field lab. A detailed look on the stress path reveals a relation between time step of the stress trajectory direction and the induced microseismic events. In other words, after failure, the microseismics develop since the stress path approaches the failure surface until it starts to go away from it. The parameters of the viscoplastic model have been manually adjusted to render a good reproduction of the earliest stage of the simulation up to 3.4 hours. We validate the model by adding more injection cycles. The numerical model reproduced the pore pressure evolution at the injection borehole very well during the validation period from 3.4 hours to until 8 hours. So we conclude that the viscoplastic model reproduced the progressive hydraulic stimulation of the fracture, which enhances permeability away from the injection well as the number of injection cycles accumulates. We choose some observation points to monitor permeability evolution along the fractures. Permeability enhancement occurs 50 meters away from the injection well in the injection cycle, around 8-hour injection, coinciding with a swarm of microseismic events. In every injection cycle, when permeability surpasses the previous achieved maximum value, microseismic events occur. A few examples are indicated with the dotted arrows. It means that the previously activated fault patch is reached, and the new reactivation is accompanied by microseismic events. For the take-home message, viscoplastic model, including dilatancy and strain softening, improves the simulation in 3 aspects. It can reproduce a special temporal couplet process of the fractured rock to hydraulic stimulation before, at the onset of the shear, and after shearing. It can predict the timestamps of microseismicity, which is concomitant to plasticity. And last but not least, it frees the modeler of the burden of dealing with the tedious manual calibration of the permeability. So let's disseminate our research to enjoy the blue sky again. Thank you very much for your attention. If you have any question, I would be happy to hear an answer.
All right. Thank you, Iman, for your great talk. And it was really interesting to see how you solved the issue. So now I can take some questions from the audience.
Okay.
So we have one question.
Okay.
So it is, can you explain better how you model the fault zone and main assumptions? Friction within the fault gorges is an important aspect controlling the fault slip. Have you considered this, and how?
Okay, let me show the model here. Okay, our method to model fault and fracture is based on a continuum approach. It is using an equivalent fracture layer. So we use a equivalent fracture layer, but we upscale the properties of the layer, such as permeability, Young modulus, Poisson ratio, and this kind of stuff. So we had monitored the geological loggings, so we knew that where are the fractured zone and what is the permeability. These are the inputs that the Pedreto lab gave us. So based on the input, we upscale the properties to fit to our equivalent continuum layers. And then we had some calibration simulation to see that if we can reproduce the fracture. So this slide. So at first, we try to use different upscaling methods and different input for our constitutive law 2 to see that we can reproduce the field data or no. So in this phase, we could reproduce the field data. So, but after that, we resume the simulation and then resume the injection process to see that, okay, the model is calibrated or no. So that was the process of choosing and calibrating input for material and the methodology for the fracture modeling.
Right. Thank you. And actually, I had one question. I don't know much about this topic, so I have pretty basic question. So in the beginning, Iman, you mentioned that some people in the society are opposed to this technology because it generates seismic activities, and the people are working to recover the damage caused by this seismic activity. And can you explain more how engineers are planning to recover the damage that was caused by such activities?
Yes, okay. This is our motivation. This is the main goal of our research group and the similar research groups, that now there are some laboratory field works that they do experimental works, and there are some research group like us that we do computational and numerical simulation. So with both field measurement and numerical simulation, we can try to develop a model for forecast seismicity, or a methodology to at least mitigate this seismicity, to reassure that the public that we can achieve this kind of technology with minimum risk. So the idea that the main drive of this kind of research group is that.
I see.
Yes. So we hope we can, we are doing that. Yeah, the idea of this, all of conferences and public outreach, is to convince the public that first we need these kind of energy resources in order to decrease our natural greenhouse gas emissions, and on the other hand, we can minimize the risk for this kind of technology.
Thank you. We had a follow-up question from the Siddhartha. It says, to be specific, what is the friction coefficient at the slip interface? How does the continuum approach to an equivalent fracture account for this?
Okay, let me see it. Can you explain better how the model? Okay, to be specific, what is the friction coefficient? The slip interface, how does the continuum approach? Okay. So the friction coefficient in the first two model is constant, is around 23 degrees. So, but in the viscoplastic model, at the peak, we had the same, but at the residual, it can decrease until 20 degree. So based on the softening parameters, it can start from 23 degree until 20 degree, based on when a slip starts, and we have plastic strain, because eta is a function of plastic strain. So when a plastic strain starts to accumulate, it decreases from linearly from 23 until 20. This is the mechanism of the softening parameter. I don't know if I can answer your question or no. I put my email at the end, so if you have further question or comments or anything, you can contact me. I would be happy for any further question or comments.
Yep. And I think we can take this last question from the audience. And so it's from Emad. Thank you, Iman. Is there any thermal monitoring after the injection in bedwetting lab?
Actually, I'm not aware of that. For sure, there are some thermal monitoring. My work was dedicated to hydromechanical coupling, but yeah, for sure they have some thermal monitoring. You can visit the website for bedwetting lab. They have published some papers on the data. I think our work is the first simulation work, but for the pure data and characterization, there are some published work on the geological characterization of sites and the monitored data. You can visit the website and their publication. For sure, they have it.
All right. Thank you, Iman, for your presentation.
Thank you very much for having us.
Yes. And I think we can conclude today's session. And before we end, I would like to announce our next session, which will take place in December 12th in 3:30 p.m. in Central Eastern Time. We'll also have two speakers in that session. From Philip Salter, exploiting induced carbonate precipitation to improve reservoir storage integrity and geothermal system efficiency. And second speaker, Julia Cerotti, pore-scale oxygen distribution impact large-scale biogeochemical processes in aquifers. And we are part of Interpore Young Academy, and here are the faces in the front and behind the scenes of PMTTT. We are composed of early career scientists across the globe, and we are looking for speakers. So if you are interested in presenting your work in PMTTT in our future sessions, please email us. Or if you know someone who's doing a great job and it will be best for them to advertise their work, please let us know, and we'll try to contact them. And thank you all for joining us today, and thank you speakers, Iman and Anna, for presenting, and see you all next time. Bye-bye.
Bye.